Okay, thank you very much, Franco, and organizers of this meeting. I've been to Africa as a tourist, but I've never given a talk as a physicist. So this is will be fun. So I'm going to talk to you about an introduction to quantum error correction with superconducting qubits and microwave photons, and try to explain to you why using photons rather than the traditional qubits is the way to go. And I'll show you data from my experimental colleagues, Rob Sholkoff and Michel Deveray. So, okay, my slides are not advancing. There we go. So the take-home message is that two tasks are much easier if you have hardware containing bosons, microwave photons. First, quantum error correction, and second, quantum simulations of physical models that contain bosons. I won't have time to talk about the latter. I'll focus here on quantum error correction. So just to remind you, we're used to dealing with qubits, which are treated as two-level systems. Most things have more than two levels, but to some approximation, we can say we have two levels. And if I have three such objects, then I would have 2 times 2 times 2 is 8 possible states that could be labeled with binary numbers like this. But if I have a so those are called discrete variable systems, say they're transmon superconducting qubits, but you can also have continuous variable systems such as microwave or mechanical oscillators. I'm going to talk about electromagnetic microwave oscillators in two-dimensional transmission lines or three-dimensional cavities. And each mode of such a system is a harmonic oscillator that can contain 0, 1, 2, 3, 4, 5, 6, 7, 8 bosons, microwave photons, and can be described by a coordinate x, which in this case is the electric field in the cavity, and a continuous wave function psi of x. So this is a very simple object. It's an aluminum box filled with vacuum, and it essentially has no moving parts. The degrees of freedom are just microwave photons living inside, and there's a very large Hilbert space for that, which does not require building more and more qubits. So that's the main advantage. So I'm going to try to explain the essence of the quantum error correction problem. This is going to be mostly a qualitative talk, but I'll be happy to answer more technical questions later. So here's the essence of the problem. I'm going to give you an unknown quantum state. Maybe I've taken it from the middle of running an algorithm on a quantum computer. I don't know what the state is. You don't know what it is. If you should measure it, it's going to change randomly due to state collapse, or what's called quantum backaction. And your task is that if it develops an error, please fix it. Well, it seems that you would have to make a measurement in order to see the error, and that will change the state. And then you will destroy it, the quantum information. But miraculously, you can actually do quantum error correction. And to me, the fact that this is possible in principle is much more amazing than the idea that you could do quantum computation on ideal hardware. This is going to allow us to do quantum computation on imperfect real-world hardware, if we can make it work in practice. So there's a no-go theorem for error correction in classical analog computation. You can only do it in digital computation, binary computation, and your a cell phone has a special chip in the front that all it does is error correction in receiving the weak signals from the cell phone towers. But quantum machines seem like they're basically analog, although they do have digital features. So we have to understand whether error correction is possible. So I like to think of quantum error correction as an adversarial game between you and a noise demon. And the noise demon has universal computational power. The noise demon can make arbitrary gate operations on let's say, a bounded number of qubits, say 1 and 2 qubit continuous gates. In order to beat the noise demon, we're going to have to require that it has bounded speed. It's not infinitely fast. And you, who are trying to run do the quantum error correction, are given less computational power. You have in this game only non-universal gates called Clifford gates and measurements. So only certain rotation angles, like 90 degrees around the Bloch sphere, are possible. Nevertheless, even though the noise demon has more power than you can win this game. You can correct the errors, provided that you are faster than the noise demon and don't make too many mistakes yourself. The problem is that we're going to do quantum error correction using hardware, which is basically the same as in the quantum computer whose errors we're trying to correct. And this error correction hardware makes mistakes itself. But surprisingly, you can still do this as long as you don't make too many mistakes in correcting the errors. So the way with qubits, the way you make a logical qubit and store quantum information for and do quantum error correction is you store the information in a logical qubit that consists of n physical qubits. So in this example is a 3x3 array of physical qubits. These might be transmon superconducting qubits or trapped ion qubits. And you have many of them. And you store the quantum information in the logical qubit in some non-local way that's entangled among all these qubits so that it's kind of hidden from the environment. The non-locality, the fact that the information is stored in correlations among different qubits, means that no single qubit can know the state of the logical qubit. So if the environment accidentally measures one of these qubits because it decays and emits a photon into the environment does not learn the state of the logical qubit. If it did, the state would collapse. And then you have to make special multi-qubit measurements that can tell you what the errors are without telling you what logical state the error occurred in. So that's the very tricky and special property. You don't want to learn the state because then the logical state, because then it'll collapse. And miraculously, quantum errors are analog, that is continuous. Like you could slowly rotate a qubit away from, on the Bloch sphere, away from where it's supposed to be. But if you measure that error, you always get a discrete result, just as when you measure a qubit, you always get 0 or 1. So this is measured errors are digital or discrete. And in this case, state collapse is our friend. You can go from a state that's a superposition of no error and some small error. And the state collapse will either make the error go away or make it into a full error that you can correct. So we have to build a Maxwell daemon to fight the noise daemon. And the Maxwell daemon has to make these multi-qubit measurements and do the error correction in a way that sort of sends the entropy caused by the noisy environment out of the quantum computer and into a cold bath. But unfortunately, the first thing that happens is if we have n physical qubits, each of which has errors, we've started off by making the error rate n times larger. So in this case, this logical qubit would have an error rate 9 times larger than a single qubit because there are 9 physical qubits in it. So the Maxwell daemon has to be so fast and so accurate in fighting the noise daemon that it can overcome this step backwards by a factor of n just to reach break even, where the lifetime of the logical qubit is the same as the best of the physical qubits. And of course, we want to do much better than that. So every quantum error correction protocol begins by taking a huge step backwards and making the error rate much worse. Then you turn on the daemon and you try to recover that factor of n and then do much better than that. And of course, the daemon can make mistakes of its own, but the trick is that it's not good, but it's not fatal, provided that the errors that the daemon makes and puts into the logical qubit are of the kind that the daemon can correct in the next round of error correction. That's called fault tolerance. So what's the definition of better? I want to define a quantity we call quantum error correction gain. So you start with a state, you run it through a quantum channel. In this case, we're using this as a quantum memory. So we want the output of the channel, that is after waiting some time, to be the original state. And so you can define the rate at which that fidelity of overlap of the remembered state with the original state decays. And then there are different error models. You can have amplitude damping and dephasing, or completely random rotations around the X, Y, and Z axes on the Bloch sphere, for example. And we define the error correction gain as the improvement in the logical error rate relative to the best error rate among the physical qubits in the logical qubit. And we define break even to be when that's 1, so that the error correction process doesn't make things worse or better. So n qubits have 2 to the n states, and we want to define logical qubit states, which is just a subset of 2 states in there, and define logical Pauli operators X, Y, and Z. And then we do this by adding n-1 constraints in the space by imposing that there are n-1 operators called stabilizers, and the code words are required to be +1 eigenstates of all of those operators. And the stabilizers have to be mutually commuting and commute with the logical operators so that you can measure them simultaneously and won't affect the logical state. but at least some of the stabilizers have to anti-commute with physical errors so that an error is flagged by this measured value of the stabilizers flipping from +1 to -1. But when that happens, you will be able to see there's an error, but it will not have damaged the logical information. So a simple example with 9 qubits is the Shor code. There are 3 types of errors, Pauli X, Y, and Z on each of 9 qubits. So there are 27 possible error states plus the no error state, so 28 altogether. And the code requires measuring 8 different stabilizers, some of which are very complicated multi-qubit operations. And this is very difficult, and is the reason that no qubit-based quantum error correction codes have yet reached break even. So we're going to talk about a new idea, which is not to use material objects to carry the information, but rather use microwave photon states stored in very high quality factor superconducting resonators. And so these are called bosonic codes. And here's a few references on this topic. So again, a given mode of a microwave resonator is a harmonic oscillator. It's very simple. It's an empty box with some electric field inside. And so I don't have 9 physical qubits, for example. I have 1 harmonic oscillator with many states. And that's going to provide what we call hardware efficiency and greatly simplify the errors that you have to correct. Because basically the only error to correct is losing a photon. You fall from 4 to 3 to 2 to 1 to 0. So we need to pick out 2 orthogonal states, some superposition of all these photon number states to provide the logical 0 and logical 1. And I'll tell you about how you do that. But first, let's think about what is the longest lived uncorrectable qubit in this oscillator. Well, I could make a qubit by just taking the 2 states of 0 photon and 1 photon. That would act like a qubit. If I lose a photon by falling from 1 to 0, that's the other code word. So there's no way I can correct this. But this has the smallest number of photons possible. And since the rate at which a damped oscillator loses energy is proportional to the energy, this is the slowest decaying pair of levels in the system. And that's the lifetime of this, the damping time of the 1 photon state, is what we have to beat in order to reach break even. So can we leverage active quantum error correction to create a logical qubit that's better than all the constituent physical qubits? So here's our system. There's a microwave resonator. There's a physical qubit, the transmon shown here. There's a readout resonator, a drive port. And this oscillator here has a longer lifetime than the transmon qubit, but transferring the quantum information from here to here is not does not constitute error correction gain. It's just using a better physical qubit, the 0-1 Fock encoding of this oscillator. And we want to do better than that. That's what we have to beat. So the simplest error model, which is pretty accurate, is that the only error is photon loss. So if I were to use code words that were made of definite photon number parity, for example, this code here has only even photon numbers in it. So 0 logical is 0 photons plus 4, 1 logical is 2 photons. If I were to do that, then all I have to measure to see whether there was an error is the photon number parity, because photon loss will change that from even to odd. And it turns out that it's very difficult to do that in ordinary quantum optics, but in circuit QED, it's relatively straightforward and can be done in a quantum non-demolition way very accurately. So here's this code. This is perhaps the simplest bosonic code called the binomial code. And it can correct up to 1 photon loss. So here are the code words, which I already showed you. And if I lose a photon, this state goes to 3 photons, and this state goes to 1. And then I need to be able to execute a unitary operation when I see the parity change that maps 3 back to this and 1 back to that, and it's possible to do that. This particular code was studied experimentally by Luyan Sun's group in China and reached 92% of the break-even point, but didn't quite reach break-even. Yep.
7 minutes. 7 minutes.
7 minutes, thank you. The first code to slightly exceed break-even was based on Schrodinger cat states, which are superpositions of coherent states plus alpha and minus alpha displaced in position or displaced in momentum. And that code, that experiment done in the Shulkoff group basically slightly exceeded break even. And if you, certain errors were heralded, and if you removed 20% of the data where you knew those errors occurred, then the lifetime gain was almost a factor of 2. So what I want to talk about now is the current record holder for quantum error correction gain. It's a very strange code called the GKP, Gottesman-Kitaev-Preskal code. And we visualize it with something called the Wigner plot. This is the phase space of the oscillator. This is the position or the electric field in the cavity. This is the momentum or the magnetic field in the cavity. And these blobs that you see here, there are roughly 35 of them. So it's kind of like a Schrodinger cat living in 35 different places in phase space at the same time. It's a very strange code, which when it was invented, nobody thought it could ever be created in practice, but now there are very important experimental progress in both ion traps from the Jonathan Holm group and in superconducting resonators from the Deveray group. So here is the latest data, quantum error correction in action. So you prepare an approximate version of the state, and after 100 cycles of error correction, the state has gotten more precise, and still more precise after 200. After 400, you can see that some of the dots are starting to fade here. And after 800 cycles, both code words, the original code words 0 logical and 1 logical, have now become indistinguishable because the system is fully mixed. So the lifetime of this error correction is about 350 cycles. And the error correction gain is about a factor of, is slightly larger than a factor of 2. And as I mentioned, the cat code was just barely larger than 1, and all other experiments with qubit surface codes and so forth are all still sitting below 1. So this is very exciting progress. But of course, we'd like to have an error correction gain of 10,000 or some huge number to make it worth the trouble of doing all of this. But we have to start somewhere, and now we're at least above 1. So that's significant experimental progress. So my take-home message is that, as I said, quantum error correction and quantum simulations of physical models containing bosons are both vastly more efficient on hardware containing native bosons. I didn't have time to talk about quantum simulations, but here's a paper on molecular vibrational spectroscopy where the calculations of the spectrum were done using boson sampling. And the bosons in this case are the vibrations of a triatomic molecule. So the GKP code experiments were done in the group of Michel Devereux. The lead experimentalists were Vlad Sivak and Alec Eichbush, shown here. And the cat code experiments were done in the Shulkoff lab. So I thank you for your attention, and I'm very happy to take questions.
Oh, thank you for a very, very nice talk. And then let me look at the chat. Here, there's a question by Afan Madhu. What are the fundamental causes of error in superconducting circuits?
Okay, that's a great question. So let's talk about qubits first. So for a qubit, you can have, the states of the qubit and the energy of the eigenstates are functions of some parameters in the Hamiltonian. And there can be noise from the environment that causes the transition frequency to change a little bit with time. That produces what's called dephasing errors of superpositions. There can be, just as an atom can spontaneously decay from the excited state by emitting a photon, superconducting qubits can spontaneously decay by emitting a microwave photon. So that's called an amplitude damping error. So those are two examples of the kinds of errors that can happen. You can have accidental terms in the Hamiltonian that couple two qubits together so that the properties of one get affected when the other qubit changes state. In microwave resonators, the frequency is very, very stable. It's just set by the machinist who made the cavity, the size of the cavity. And but even though they have a Q of 10 to 100 million, these are still damped oscillators, and there are occasional, about every millisecond or so, photon losses, and that's the primary error that we have to worry about in sonic codes.
Oh, great, thanks. A question I have is the following, no? You mentioned very exciting results on the GKP code, the four-leg cat code, the surface code. Among these different flavors, which one do you think might be more promising, or there might have different niche, let's say one niche GKP code, another niche the cat code? How would you see this going forward, essentially? Which one might be more promising in the future?
Well, I think what we're looking at for the future is to build a surface code out of a set of qubits, which are themselves bosonic logical qubits. So you could have an array of resonators, and inside the resonator, you could have quantum error correction with a GKP code or a binomial code or a CAT code that will make the error rate very low, putting it way below the fault tolerance threshold for the surface code. Then you put an array of such logical qubits in a sort of second layer of error correction. And that if you're well below the threshold for the surface code, you do not need a huge surface code with 1 million qubits. Maybe just a small surface code with 17 qubits will now give you extremely large error correction gain. So we think the future is to have one layer, the base layer, be logical bosonic qubits, and the next layer be your favorite next qubit code like the surface code.
If these techniques, which are very interesting and exciting, they were to be complemented and supplemented by machine learning, will that help to reduce the requirement on number of qubits? Is that something that makes sense to mix this together to?
Sure. So machine learning has several applications. One is you can try to optimize the error correction protocol. The error correction protocol consists of making lots and lots of measurements, taking in huge amounts of data and deciding what it means for the errors and how to fix them. So machine learning can be used to improve the decoding process for the surface code, for example. And it's good for learning precisely what the error model is that you're correcting. And actually in the Deborah experiment, machine learning, reinforcement learning was heavily used to optimize all the control settings in the experiment. And it turned out to be vital to getting from a gain of 1 to a gain of 2. So the reinforcement learning measured the error correction gain over a period of 4 hours and turned roughly 30 knobs, modified 30 parameters in the error correction protocol, and found the best settings to give the maximum gain. And that turned out to be absolutely vital, because you can do the best job you can calibrating, but 30 knobs is too many for one person to turn.
Especially when they need to be turned at the same time in different directions. So
exactly. It's a 32-dimensional space. It's pretty big.
No, this is an exciting combination of surface code and machine learning. Somebody has a question there, somebody?
Yeah, I was curious if you'd care to comment on when you think we'll see demonstrations of 2-qubit gates in these GKP codes.
Excellent question. It's next on our list. The GKP codes have these very nice property that Clifford operations are just Gaussian linear optics operations on the bosonic code words. So we're hoping to do a C0 gate using a combination of using what's called a sum gate, which is a simultaneous beam splitter and 2-mode squeezer between 2 cavities containing GKP states. So that's the very next experiment that's being set up now.
Would that gate be fault tolerant if you did it that way?
Well, we have to have a discussion about what you mean precisely by fault tolerant, but the dominant fault for us is the fact that we have to have we don't just have oscillators, we have to gain control over them, we need ancilla transmon qubits. And those are the dominant sources of error. And there are tricks using higher levels of the transmon to make the operations tolerant of faults in the transmon. So that we know how to do. And that may be good enough to get us to pretty high fidelity gates.
Yeah, and then leverage the service code on COP to take you the rest of the way. Thank you.
Exactly, exactly.
Sorry, let me ask you a simple question. So in the plot you showed, there was GKP1 and there's 2. So what's the difference?
So GKP1 is the first experiment from the Deveray group, which approximately reached break even. And GKP2 is unpublished data, just fresh from the last few weeks, in which an improved transmon ancilla made with tantalum was used in the experiment, and the machine learning process was improved and so forth. So it's just the most recent improved experiment.
Okay, thank you very much.
Yes.
Any more questions? Tantalum is the qubit is made of tantalum?
No, the qubit is made of aluminum, but it's a small object that's more easily lithographed, and it's coupled to the capacitor pads are the tantalum. And it's not really clear why these are better. This is where several groups are looking at this, including a Princeton group. Tantalum's easier to clean. The fact that the aluminum object is now smaller makes it easier to make more uniform controlled lithography. Tantalum might have better properties sticking to sapphire. Maybe Will has an opinion on this question.
I think it's still TBD. I agree with Steve. I think a lot of groups working on it. We're working on it too, but it has some advantages that there's process independence. So it doesn't etch necessarily in the same chemicals that aluminum does. So that's a practical reason to do it. But currently our aluminum devices are about the same T1s, 200 to 300 microseconds as our tantalum. And so it's not clear to us yet, what's the origin of this advances that some groups have seen, but nonetheless, they've seen them, and that's a good sign.
Right.
Okay. Thank you very much, Professor GIRVIN. Yep.
Thanks for the great talk. Fantastic. Excellent.
Thank you.